Next presentation will be given by Erin Komi. She comes from Etteplan. So Etteplan has put recently a lot of efforts in the field of AM design, and so she will kind of talk about the design principles and the tools needed for the to make a good designs for AM. So Erin, please.
Sorry, can you hear me now?
I can hear you well.
Okay, perfectly. And you can see my screen. Can you see me?
Not
No.
yet.
Sorry about this. I'm missing the button. Do I need to, it says start video, but it's not video, it's is it okay if I start without showing me?
Please go ahead.
Okay. Apologies for these technical difficulties today. But anyways, hi, I'm Erin Komi, and I am coming from Etteplan's Additive Manufacturing and Optimization team, where I work as an AM specialist, and I focus primarily in my particular job as sort of a simulation expert for additive manufacturing in particular. So simulation related both to the design and then also to the printing process itself. And so today I'm going to give a rather general overview of our approach to AM design. And so before I get into that, I would like to give a little bit of a background or overview of my company, Etteplan. So we're an engineering services company operating in Finland, Sweden, Central Europe, and China. And we have over 3,500 employees, and we have three service areas that include engineering solutions, software and embedded solutions, and technical documentation. And if we're looking or thinking about our additive manufacturing and optimization team itself, while we have been doing AM in Etteplan for more than a decade, actually, we formed the team at the beginning of 2017, and this we call it the AMO team, and we're standing for Additive Manufacturing and Optimization. And this team now consists of 6 core team members that are all AM specialists and our business manager. And we have also trained over 20 of our own designers and calculation experts on AM technologies and design. We also have a wide variety of skills within our team that include areas of AM materials, methods, and machines, AM factory design, AM product design, and simulation. And our offerings in AM in our AM services sort of reflect this broad skill set. And our strengths come generally from our tradition of strong cooperation with our customers, our knowledge in simulation-driven design for additive manufacturing, and our ability to identify strong AM business cases, and then our extensive partner network. And when I'm saying our partner network, I'm thinking of the service bureaus that we're working with to print the parts, the actual machine manufacturers, these AM machine, I mean, the powder suppliers, and so on. We are also trying to constantly develop ourselves and also to push additive manufacturing forward in our region of the world. And some examples of this include a very large internal AM development project, which started already when our team was formed in 2017 and still continues to this day. And among other things, we have developed as part of this project the AMO tool, for cost estimation of parts for laser powder bed fusion. And we were proud to recently release this tool publicly, and it can be used now online for free. And you can see the website there on the bottom left of the screen if you want to try it out yourselves. We've also been developing what we call this AM quality pyramid. And this is a tool that we have been using to help us define the information and the steps that are needed to design and manufacture to a case-specific quality level. And this again has been done in cooperation with our partner networks as well. So this isn't just an internal project, but it started with this internal study and has been expanded. And then finally, we have been consulting the Finnish government and defense forces with projects such as this HX project, where we did this feasibility study for an AM Center of Excellence in Finland. Now to get back to sort of the main topic of today, I wanted to start by showing the two key guiding principles that Etteplan uses when it comes to AM projects. And the first of these on the left is essentially the MOT model, and that's that added value comes from design. And so we believe that in order to fully take advantage of the geometric freedoms that AM offers us, we need to design specifically for this manufacturing method. And so we prefer to use simulation and advanced 3D modeling to design for function and performance as each individual case might dictate. And the second idea is that teamwork or close cooperation with our customers, our mechanical design engineers and simulation experts within Etteplan, and the network of print service bureaus, machine manufacturers, powder suppliers, and so on is absolutely key to successful AM design. And so with these two things in mind, today I will discuss some of the people or areas of expertise and the tools that are needed for AM design in general. And then I'll go over 3 different customer cases where I will describe how we put this into practice. And so to start out, this is what our typical AM design workflow looks like. So we start by working really closely with our customer to create a good business case, utilizing, for example, the AMO tool to estimate the cost and return of investment of the case before design work even begins. Then we start to review the data or the starting data for the case. And we choose the manufacturing method and the material that will be used for that case as early as possible in order to freeze the process in order to guarantee the needed quality level for the end component. Then we start the typically iterative process of ideation and concept creation, where our work is driven by a combination of simulation and experience. Once the final concept is chosen, then we tend to move to the detailed design phase, and this is followed by a final design validation and then delivery of, for example, the geometries and the drawings to the manufacturer to be produced. And so we start each of these AM design projects by assembling a team and working out what simulation and modeling tools will be necessary to complete the job. And so here are some of the key roles that we tend to use in our AM projects. And we try to eliminate these sort of internal silos and have developed a more agile and effective way of working. And this is done by creating very project-specific teams based on the fields of expertise that are needed for a given case. And so some of these roles include the product expert, and the product expert is often coming from the customer side, who we like to work very closely with in most of our design projects. We also need a strong understanding of the chosen AM method and, for example, the needed post-processing, as well as the relevant material information and design approach for that technology. So then we have experts in AM methods, materials, and AM design. We also work really closely with our engineering analysis team, where we have structural, thermal, and fluid dynamic experts that join many of our projects. And then finally, in nearly all of the cases where laser powder bed fusion is used, then we have an AM process simulation expert to ensure that even our most complex designs will be printable. Here's a look at some of the simulation and design tools we're using in our AM projects. So finite element analyses and computational fluid dynamics are often used at the beginning of a design project to evaluate existing structure and fluid flow in designs. And then throughout the project to guide new designs and to ensure that we're meeting all performance targets. We're also using topology optimization and generative design early in the design process to optimize the use of material for known or assumed loadings. Then we're using advanced 3D modeling to try to take advantage of the geometric freedoms offered by AM. And so, for example, this might include using lattice structures or some type of bionic design to add new functionality or reduce weight, or to create and modify the organic structures resulting from a topology optimization. Finally, print process simulation is used to guide us to find best part orientation on the build platform, to create and optimize support structures, predict recoder blade collision and other build failures, and estimate distortions and stresses and so on of the part after the build. And so there are a lot of dedicated software tools for AM design and AM simulation with new features and seemingly more players coming to the market almost every day. And so here you can see a list that AMFG made describing the software available for both design and process simulation last year, with some additions that came in the 2020 list as well. So you can see there's a rather wide variety of tools that you can use. And from our experience so far, there isn't a single one tool or system that can be used to do everything when it comes to AM design. So it's usually picking and choosing the best tool for each given case. So now I'll move on to these real cases that we have, so I can actually give a better, well, show what we're actually doing and how we're using these experts and tools. And so to start with, I will look at a hydraulic block that we created for John Deere. And this is a hydraulic block that is positioned on the boom of a tree harvester. And we were asked to redesign this part to really take advantage of additive manufacturing. The goals were to modify the internal channels so that they would be able to decrease the pressure drop. And as this is located on a boom, they wanted us to reduce the weight if possible. Also, size reduction would be useful to make assembly of this part and the surrounding parts a little bit easier. And finally, we were supposed to do our best to keep manufacturing costs as low as possible. And so here on the right hand of the slide, you can see a summary of the experts needed within our design team, as well as the tools utilized. And then on the left is sort of a summary of the design approach we took. And so for this case, the design of the hydraulic block was really driven by the optimization of the internal channels. So computational fluid dynamics was used to evaluate flow and pressure drop, both in the original design and then all of the channel concepts that were considered. The final channel concept was then chosen based on a combination of the lowest possible pressure drop and also printability, because when printing a part with internal channels, the structure always needs to be self-supporting because it's essentially impossible to remove support structures later on. And so in order to achieve this, we had a really close cooperation between our AM design expert and the CFD analyst on this case. And then once this sort of best option was selected, the concept was then further fine-tuned to improve the performance and still maintain the printability. So then the next step was to start to build the rest of this hydraulic block around these channels. And here we used finite element analyses to analyze the strength and the performance of this new design, and to go throughout the part and optimize the wall thickness to be as thin as possible where the loads were low, but then to be thick enough in other regions, and to also determine locations and dimensions of needed rib structures that were added during the final fine tuning of the design. And then in the end, and actually at several stages throughout, we use print process simulation to do many things, including help to position the component, analyze where support structures would be needed and how dense they should be, and then to essentially guarantee the printability of the part. And so by working in this way, we were able to create a unique channel geometry that reduces the pressure drop by 40% while being printable and still working well with high velocity flow going in both directions. And we were also able to reduce the mass by 60% and have an overall size reduction that allows for easier assembly of this and surrounding parts. Our second case is coming from Wärtsilä, and this component is part of a pressing tool assembly that was meant for the installation of cylinder head valves on one of their new engines. And so initially this part was meant to be machined and then welded, and you can see the part on the bottom right there as initially designed. But after some finite element analysis method calculations, we saw that the part would be unsafe as it would not be able to take the high forces occurring during use. And so then this part came to us, and we were asked to redesign this part for additive manufacturing. And because they needed it immediately, they wanted us to do it as quickly as possible and within a set manufacturing budget. And so in this case, they wanted to keep the total manufacturing cost below €1,000. And here you can see also approximate size of the part. And initially there were 3 material options, and this is because they had predetermined the service bureau that would be printing the part. So those were the 3 materials being offered by them at that time. And so for this case, topology optimization was used to guide the design because we wanted to optimize the use of material and to create a self-supporting structure in order that we could minimize the printing and post-processing costs. After running the topology optimization, we used finite element analysis to evaluate those initial results. And we used it again later to ensure that the final component design could be used safely. Advanced 3D modeling was used to interpret the chosen design variation and to create the final structure. And then print process simulation showed that the part could be printed as designed with low distortion levels. And so the benefits that we're seeing from taking this type of design approach include having a design that was ready for the manufacturer in under 1 week from the time that the starting data was set by the customer. Also, we were able to keep the manufacturing costs within budget by optimizing the use of material and creating this structure that was almost entirely self-supporting. And now we have a tool that is safe to use for the installation of the cylinder head valves. Our last case today is a component coming from Rosendahl Nextrom. And I'm not allowed to share the exact function of this particular part, but I I can say that this part was made of aluminum and is existing in a hostile environment with temperatures over 1000 degrees Celsius. And in order to sort of survive in that environment, there are cooling channels with circulating water that are needed to keep the temperature of the part below melting point. And so the image on the right here is showing this initial design coming from the customer. So the blue is showing the cooling channels, and the transparent, I guess, is the rest of the design. So this is the whole component there. And basically the issue here was that this part was extremely difficult to manufacture. The original part had 8 components with 11 welds, and machining was needed after each of those welds. And because they weren't able to manufacture this easily, they came to us and asked that if additive manufacturing could be used to improve this manufacturability, with the hope of also consolidating some of the parts and reducing the amount of welding that was necessary. And so our approach for this case differs from the previous examples because the design was guided more by experience in this case than simulation. And so the cooling channels were designed in close cooperation with the customer, who had a lot of experience with this and similar components. And our AM design expert in this case was also trained in design for manufacturing and assembly. So DFMA principles were also used to guide the design. And this led to a sort of hybrid manufacturing approach. So additive manufacturing was used where necessary. So for example, in these complex geometries where the cooling channels were located, but then more traditional manufacturing methods were used elsewhere. And so in the end, we had 3 parts that were printed in blue. They're shown on the left. So on the top left, and there was the central part, and then on the bottom left, there's another piece that we print 2 of those, one for the top and one for the bottom, but the part was designed so that it's identical on both ends. And then there were 2 traditionally manufactured parts shown in purple. And here it's describing the whole process. So we were also, as I mentioned, trying to minimize the amount of machining. And so the machine surfaces you can see are shown in orange. And the number of welds was also significantly reduced by using this approach. In addition, it's not shown here, but we used print process simulation to analyze those parts made by laser powder bed fusion to again ensure the printability and to minimize the need for support structures. And so by following this approach, the benefits that we gained was that we had a significant reduction in the number of manufactured parts, so going from 8 to 5, the number of needed welds, it went from 11 to 2, the frequency of machining throughout the process, and we also had a mass reduction. It went from 5.8 to 4.3 kilograms. And so now this component can be integrated or can have the needed integrated cooling system, but still be successfully manufactured. Okay, so that's all I have for today. Thank you for your time and attention. I'm very happy to take any questions, and also I was a bit late in this, but I have reserved a Teams meeting after this as well, where I can answer questions as well.
So thank you very much, Erin. Really nice presentation you gave, and as you said, you are available during the next break. So there is a link in the chat box where you can then connect to this separate discussion. I have one question for you. So you really emphasize the kind of networked way of working here, and also then it's not just a network of experts, but it's a kind of network of softwares. So you need really quite many softwares to kind of achieve your goals. So my question is that what is the currently kind of status of the compatibility of the softwares? As we know, at least in the past, there has been some challenges how to change the model from the one program to the other one. So, for instance, if you are combining FEM-based or computational fluid dynamics-based approaches, how well this can be done nowadays?
I think that it's constantly moving forward. It's constantly getting easier, and so the problems that we saw several years ago, I think many of those have been addressed, and there are more and more tools available where you can stay more or less in a single environment to do your, the finite element analysis or the topology optimization, and you can do the advanced 3D modeling and that sort of thing. But I think there's a bigger difficulty, I would say, rather than going from one software to another, in sort of converting file types for the final print component. Because STL file is still used so prevalently for the actual printed part, I think that we see bigger issues when it comes to sort of like quality control and human error when it comes from changing like these standard CAD files. So for example, step format to STL. I think that's where we have more problems than maybe jumping between, the FEM software and CFD and, these 3D modeling tools. But with that being said, I would say that it's so much easier now than it was 3 or 4 years ago. And it's improving all the time.
Well, that's good to hear.
Yeah.
Certainly, yes.